Okay, now let's move to postulate 3. In continuous time sinusoid, it said that um, as we increase the frequency of a continuous time sinusoid, the rate of oscillation keeps on increasing, which allowed us the frequency range of minus infinity to plus infinity. Now here in discrete time sinusoid, the postulate is saying that the highest rate of oscillation in a discrete time sinusoid occurs at frequency equals to half or omega equals to pi. This is a very, again, a different observation. In continuous time, the highest rate of oscillation is at frequency equals to infinity, whereas in discrete time sinusoid, it is claiming that the highest rate of oscillation occurs at frequency is equal to half. Now let's look at some numerical examples to see whether this is true, and if it is true, then what are the options for us and how to proceed further. Okay, so these are, instead of 1, 2, 3, there are 7 examples. The examples differ again in terms of FD. In example 1, the frequency is 0. In example 2, the frequency is increased to 1 over 6. In example 3, the frequency is further increased to 1 over 3. Then it is further increased to half, 0.5. Then in example 5, it is further increased to 2 over 3. Then it is further increased to 5 over 6. And lastly, it is further increased to 1. Of course, we can go on. But I think this is sufficient for us to make the important observations. So when coming back to example 1, so when the frequency is 0, the signal returns the value as 1.0, 1.0, 1.0, 11111. We know that when the frequency is 0, the signal becomes a DC signal. Now keep an eye on the rate of oscillation. Rate of oscillation we can observe by looking at the difference of 2 consecutive samples. So there is no difference between the 2 consecutive samples. The rate of oscillation is minimal. There is no change in the oscillations. There is no oscillation, in fact. So with the frequency, we got these values 1, 1, 1, 1, 1. Now in the second example, we have 1 over 6 FD. The values are 1.5, minus 0.5, minus 1. So 1 is the maximum value which can happen in a cosine, and minus 1 is the minimum value which can happen in a cosine. So it takes almost 3 samples or 4 samples to move from the highest point to the lowest point. So this gives us an indication of the rate of oscillation, that yes, it is there, and it is about 3 to 4 samples. Now when we move to 1 over 3, then we have 1, then minus 0.5, minus 0.5, 1, minus 0.5. So here the rate of oscillation is further increased. Here the rate of oscillation was 1 to 0.5. So the difference was 0.5. And 0.5 to minus 0.5, the difference was 1. But here the difference is 1.5. 1 to minus 0.5 is 1.5. Although there is no difference here, but then again minus 0.5 to 1, it is the difference of 1.5. So rate of oscillation is further increased, which is as expected, that when we increase the frequency, the rate of oscillation should increase. And as we go to FD equals to half, which is further increased, then the first sample value is 1.0, the second is minus 1.0, the third one is 1, and the fourth is minus 1.0, and so on. And this is the maximum rate of oscillation we are getting, that in consecutive samples we are 1, minus 1, 1, minus 1, 1, minus 1. So this is the maximum rate of oscillation one can expect, because there is no way you can increase the rate of oscillation even further, because in sinusoids the highest value is 1 and the minimum value is the lowest value is minus 1. And the observation, interesting observation, is as we move further, the frequency is further increased, to 2 by 3, then the rate of oscillation is decreased. It's 1 minus 0.5 minus 0.5 is similar to what happened at 1 upon 3. And similarly, if you look at 5 by 6, 1 minus 1.5 minus 0.5, these values are the same as when FD was 1 over 6. So when we are moving ahead from 1 by 2 onwards, then the rate of oscillation is started to decrease, and when FD is equal to 1 is again 1 1 1 1 1, which is what we were having as 0. Now these observations are giving us an indication that yes, the rate of oscillation starts increasing from FD equals to 0, but they only increase till FD equals to half, and after FD equals to half, when you increase the frequency, the rate of oscillation does not increase, rather it starts decreasing. And in this figure also you can see that this is FD equals to 0, this is FD equals to 1 over 6, this is FD equals to 1 over 3, this is FD equals to half with maximum oscillation, and as we move further the oscillations starts decreasing again. So the postulate 3 indicates us that rather than when we compare with the continuous time sinusoid, when the rate of oscillations were increasing as we increase the frequency and there was no limit, in discrete time sinusoid there is a limit of FD equals to half, and the rate of oscillation is highest at FD equals to half, and when we go beyond FD equals to half, the rate of oscillation starts decreasing. Okay, to conclude the observations and the results we deduce from studying the postulates, the 3 postulates from the discrete time sinusoids, we come down to this, that as we increase the frequency of discrete time sinusoid from 0 to half, this is pi because here it is talking about in terms of omega. If we are talking about in terms of FD, it will be half. The rate of oscillation increases. Similarly, we note that as we move further, the oscillation starts to decrease and goes back to 0 at omega equals to 2 pi or FD equals to 1. So after observing this, we decide for ourselves that this is important. We decide for ourselves that because frequencies are generating identical waveforms, there are different frequencies and they are identical, they are generating identical waveforms, which is problem number 1 for us. And problem number 2 for us in discrete time sinusoid is that we expect that when we increase the frequency, the rate of oscillation should increase, but it is only happening till FD equals to half. We apply a rule on ourselves that okay, if we want to satisfactorily perform operations in discrete time domain, then we will have to follow this rule that frequency will have to be limited between 0 and half, because between 0 and half there is no repetition of the signal, there is no problem of the signals repeating themselves, and also between 0 and half the frequency keeps on increasing as we reach FD equals to half. So both of the problems are solved if we limit ourselves within the range of 0 and half, and obviously to make the mathematical symmetry work, we expand the range from FD as minus half to plus half, and this is a rule which is we are setting on ourselves. So whenever we work in the discrete time sinusoid, we will limit ourselves to this frequency range where FD is minus half to plus half, and if we want to read this in terms of omega, then this will be minus pi to plus pi because omega is equal to 2 pi FD. Now, I'm sure there are certain questions that as to why are we sticking to these rules. So obviously we will be discussing that in the interactive session, and also when we look at the reading assignments and the reading assignment of the book, we will be able to understand more clearly why and how this range came to be. Right, so quickly to review this lecture, we have learned that not every discrete time sinusoid will be periodic. Only those will be periodic where FD is a rational number. Similarly, we have observed that discrete time sinusoids with different frequencies can generate identical waveforms. And we now know that this identical generation of waveform happens when the difference of the frequency is integer multiple of 2 pi. We have also seen that in discrete time sinusoids, the maximum rate of oscillation occurs at FD equals to half. And looking at all these three observations, we have set upon ourselves a rule that the correct operating range for FD will be between -half and half cycle per sample. And we will be learning more about this in the next weeks. And to move towards the reading for this video, we will have to read section 1.3, subsections 1.3.1 and subsection 1.3.2, where the concept of frequency in continuous time and discrete time signals has been discussed. So with that, I wish you best of luck. Make sure that you give in your best to these videos. I've tried to keep my pace as slow as possible, and when we interact in week 2 on Wednesday, then inshallah we will be able to listen to your queries, resolve them, and please expect that I will be asking a few questions randomly with some of you people, and I hope you will be able to answer them to the satisfaction of the cohort. So again, best wishes. Thank you.